In our previous video, we learned about stress and the concept of stress transformation. And one of the ways we learned about it is the idea of taking a stress element and sectioning it along a particular angle, phi. Now, what if instead of sectioning it only at one angle, what if we took our geometry and sectioned it at every conceivable angle over 360 degrees? If we were to do that, we can generate something that's called Mohr's circle, which is a diagram which represents the state of internal, normal, and shear stresses at every direction through a stress element, right? So Mohr's circle is just that. It's a graphical representation of the state of stress, the normal and shear stresses, at every possible angle. Mohr's circle is drawn in terms of stress space, where x and y, those axes, represent the values of normal stress and shear stress, respectively. Where the x-axis is normal stress and the y-axis is shear stress, with the counterclockwise or positive shear stress represented below the y-axis. So positive shear stress is actually the negative y-axis in the diagram. I know, a little bit confusing, but Mohr's circle is a bit complicated. Let's look at an example of what a Mohr's circle looks like, and let's note a couple of the key features in a Mohr's circle diagram. We see the axes here, the x-axis, normal stress, the y-axis shear stress with positive shear stress on the negative y side of things. And then in the diagram itself, we've got a whole bunch of different features and things that we can calculate. A few key things to note are the principal stresses. Our principal stresses exist where normal stress is maximized and shear stress is equal to 0. So our principal stresses are right on the x-axis, sigma 1 and sigma 2. Our extreme value shear stresses, where shear stress is maximized and normal stress is average, those exist on the tops and the bottoms of our circle. So this is where our extreme value shear stresses are with an average normal stress that's applied to them, right? So average normal stress is sitting here. And then we have the original state of stress. If our body or our stress element was not cut, what line does that pass through in Mohr's circle? And so to draw that, let's see here, let me draw a shape. We would draw a line that represents our original state of stress, where we have sigma x, tau xy, and we have sigma y, tau xy, right? Original state of stress. And then finally, the angle of rotation. The angle, if we wanted to find the angle between our original state of stress and the first principal stress, that angle 2 times phi p is the distance from our original state of stress line to the location of sigma 1 of the first principal stress, right? So this Mohr circle, there's a lot of things that we can put on it. It gives us a ton of information. It's every potential angle plotted over 360 degrees. So then let's break it down. Let's start one step at a time, and let's build a Mohr circle diagram for any given problem. The first thing to do in drawing Mohr circle is to just draw the coordinate system. So just to note that our x-axis is normal stress, and our y-axis is shear stress, with positive shear stress being below the y-axis and negative shear stress being above it. Starting point, step 0, so to speak, for Mohr's circle. Our second step is then to calculate where the center of our circle is and the radius of our circle. The center of the circle is where our average normal stress is. So sigma x plus sigma y divided by 2, that is the center. And in terms of shear stress, 0. The radius of our circle, is equal to tau 1 and 2. It's actually the value of the extreme valued shear stresses. So our center, fairly simple, the average, and our radius, plus or minus tau 1, 2, is equal to plus or minus that square root term that we learned in the previous video. So once we've calculated our radius, we can then simply just plot the points where tau 1 exists and where tau 2 exists. And then if we've got a protractor, we can just draw a circle, right? Take the center point, take our pencil, and draw the circle. Now the next step is to identify where our principal stresses exist, and also to just note the extreme value shear stresses, which we've basically already found, and just place those points on Mohr's circle. Our principal stresses, sigma 1 and 2, those are equal to C plus R, the center, or the average normal stress, plus the radius, or minus the radius. And those extreme values of normal stress have 0 shear stress. So we can just place those dots, put a dot here, put a dot there. It's not too bad. And then tau 1 and 2, they have an average normal stress, so C, and then they're just equal to the radius of our diagram. So then we can put those points on Mohr's circle. So now we've got a lot of the information that we need for Mohr's circle just by finding these critical points. All right. So now let's do the hard part. This is probably the harder thing to do, which is locating the original state of stress. What line gives us the plus x and plus y plane of our original state of stress? We need to find that location. In order to do that, we're going to take our stress tensor, the stress tensor that we have, 2D stress, and we are going to literally look for the values of tau xy and sigma x. We're going to look for the values of sigma y and tau xy, and we're just going to plot those points where they exist on Mohr's circle, and then draw a line that connects those points. That's all we're going to do. So whatever the value of sigma x and sigma y are, will tell us something about where we are along the x-axis. And then whatever the sense of tau xy is it a positive shear stress or a negative? If it's positive shear stress, it's below the y-axis. And if it's a negative shear stress, it's above it. And let's remember the sign convention in our previous video, where if we're on the positive x surface of our stress element, if our shear stress makes us want to rotate counterclockwise, then we have a positive shear stress, which we then plot below the y-axis. All right, so now we've got our original state of stress. Now finally, we may want to find the angles from our original state of stress to where the principal stresses exist, or where the extreme valued shear stresses exist. We may want to find those angles. How do we find them? Well, we simply take our original state of stress line and we plot, or we try to do trigonometry to find the angle between our original state of stress and the first principal point, or the angle between our original state of stress and the extreme valued shear stress point, right? If we can find that angle, then that will tell us the angle with respect to our original state of stress, right? We can actually find those angles using trig. Now let's do an example here. So let's consider we've got that original state of stress. So this is our positive x surface point, and we want to find the angle from our original state of stress to the first principal stress. That angle is going to be between our red line and our black line. The distance, if we consider the red line as a right triangle, the distance here is sigma x minus the average stress. So it's sigma x minus sigma y divided by 2. our height here from the black line to, so our y component of the triangle is tau xy. And so we can then solve using tan, the tan function, which is opposite over adjacent, and we'll get a tan of 2 phi p is equal to 2 times tau xy divided by sigma x minus sigma y. So in essence, we've solved for the tan equation using trigonometry. Similarly, we can do a little bit of trig to find the angle for phi s1, where it's tan of 2 times phi s is equal to negative sigma x minus sigma y divided by 2 times tau xy, right? So that we can rearrange and solve for those angles using trig. And that's pretty much it. That's pretty much how we make Mohr circle, starting with the coordinate system, putting each individual important point. The tricky part is finding our original state of stress, and then solving for the angles, the principal stress angles and extreme value shear stress angles. Some important things to note. Mohr's circle looks different for every problem. The state of stress, the original state of stress, for one problem to the next is going to be different. So it is not going to look exactly the same. That original state of stress line could be at any particular angle. The values of principal stresses, extreme value shear stresses, the original state of stress, and the directions that we get are also unique for every problem, right? So we actually have to draw. We actually have to go through the steps to build a Mohr circle specific for our problem. And then finally, to draw a Mohr circle correctly, we must actually input the numerical values into our diagram. So we actually have to solve these equations. And so what is sigma 1? It is equal to a number, right? Just leaving Mohr circle as just symbols, so just making a Mohr circle that looks exactly like this, is not actually drawing the Mohr circle for your problem. You're just making a diagram. So we've got to make sure to actually put the numbers in where they go on our Mohr circle diagram for our problems. And that's pretty much it. We know how to make a Mohr circle diagram now.